So in lecture number 25, we studied how to quantify entanglement. There are several ways of quantifying entanglement, but we mainly looked at one such measure, which is called the entanglement of formation. So first we started with a two-particle pure state. So for a two-particle pure state in any dimension, it can be written as a two-dimensional summation. That's the two-particle pure state. Now, a two-particle pure state can always be written in a Schmidt decomposed form. So, a Schmidt decomposed form is essentially finding a basis. For example, here phi I tilde A for particle A, phi I tilde B for particle B. So, Schmidt decomposed form is finding a basis phi tilde A and phi I tilde B, in which this double summation turns into just a single summation. And of course, the Ci square, it has to equal to 1. So, a two-particle state, which is in general a two-dimensional sum, can always be written in this form, and once it is expressed in this form, then the entanglement of formation of a two-particle pure state is given by this formula, which is minus I to n Ci square log Ci square. So, this is for a two-particle state in any dimension. Now, what about two-particle mixed state? So, two-particle mixed state, the entanglement of formation derivation goes like this. First, we realize that a two-particle mixed state can be written as a mixture of two-particle pure state. For example, this is a diagonal representation. We have this two-particle mixed state rho written as a mixture of several two-particle pure state rho I and pi. These are the weightage. And of course, this psi I, these are the pure states corresponding to this pure two-particle density matrix, and these different psi i's are orthogonal to each other. So that's a diagonal decomposition, and that's a unique decomposition. But a two-particle pure state can have several other ways that it can be written as a mixture of pure state. So for example, if we don't put any restriction on how many sums that can be in this, how many terms that can be there in this summation. For example, here the number of terms in this summation is equal to the maximum number of terms that can be in this summation is equal to the dimensionality. But when m can even be larger than n, then when there is no such restriction, there can be several ways in which a two-particle mixed state can be written as a mixture of two-particle pure state. Of course, here the restriction is not even that the psi j, different psi j or different psi j corresponding to this rho j, they need not even be orthogonal. So in this kind of decomposition, different psi j's corresponding to this rho j's are not even orthogonal, and m can even be larger than m. So with this, there can be several ways in which a two-particle mixed state can be written as a mixture of two-particle pure state. And of course, if you have those restrictions that the different psi i's have to be orthogonal, the maximum dimensionality is n, then that's a unique decomposition, and that's the diagonal decomposition. Okay, so once we have a two-particle mixed state written as a mixture of two-particle pure state, then the entanglement of formation is defined like this. Of course, the entanglement formation of the pure state is just E rho j or psi j, the way we want to express, which is given by this formula. And then this Pj is the weightage of the pure state in the mixture, and then sum over all those states. Now, since rho could be written as there can be different representation of rho, the entanglement formation is defined as the minimum of this quantity over all such decomposition. So this minimum need not be associated with this diagonal representation. It could be with some other decomposition. So entanglement formation is defined as the minimum of this quantity over all such possible decomposition. Now, this is in general a very difficult problem, but it was shown by William Wouters that if it's a 2-qubit state, that means a two-particle and in which each particle lives in a two-dimensional space. So for 2-qubit mixed state, one can derive a formula for this quantity, and it goes like this: that for a given mixed state rho, one construct this rho tilde, where sigma y's are is the Pauli matrix, then constructs a new matrix rho tilde, finds the eigenvalue, arranges them in the descending order, and then the concurrence of the mixed state or the entangled mixed state is given by this formula, which is the maximum of 0 or this quantity. So this is a generic formula. That means for a 2-qubit state, we can find the entanglement for a generic state, mixed state. But for a general two-particle n-dimensional state, we know how to calculate it for pure state. But for a mixed state, it is in general a difficult minimization problem. So the formula is for n dimensional state, the formula is given only in this manner. Okay, so let's get started with the applications of quantum entanglement. So we had looked at this Hongo-Mandel effect, and in this effect we had two entangled particles arriving at a beam splitter and then getting detected at this two pair of detectors. So there are two ways in which the photons can get to the detector. That's one in which both the photons get transmitted. In the second one, both the photons get reflected. In this one, one gets reflected, one transmitted, and then vice versa. And then it turns out that when x is 0, that means this path length and this path length, these two are exactly equal, then these two alternatives are not there and we are left with only these two alternatives, and as a result we get a null in the coincidence counted when x is equal to 0. So that's a Hongo-Mandel effect. So in this one, what we are seeing that both the photons either go this way or go that way. So this effect can be actually be used for doing lithography with higher resolution, and this is what we will see how. So this was a paper that actually showed how this effect can be used for lithography. Okay, so first what is the classical way in which the lithography is done? So lithography is all about writing a pattern on a substrate. So here if we have a one photon state coming in, then and there's a beam splitter, so it gets divided, it gets divided into two. That means the photon can either go this way or go that way. And in this case, if we write the so this is applicable also for the classical field, not only for the one photon field. So when theta is almost 90 degree, when this coming at the grazing incidence, then the electric field right at the substrate can be written as e to the I kx, that's a field coming from this direction, e to the minus I kx, that's a field in this direction. And if you put it together and do the absolute square, that gives us the intensity, which is twice 1 plus cosine 2 kx. Or we can see that the intensity is proportional 1 plus cosine 4 pi x by lambda, where we have just written k as 2 pi by lambda. So this is the form of the intensity. So if we plot the intensity as a function of x, that is that is a location on the substrate, then we see that the intensity looks like this, that is 1 plus cosine 4 pi x by lambda. So in a lithography, of course, one exposes a substrate with this kind of intensity pattern, and whatever is intensity pattern, then that much of the material is burnt in that substrate, and when it is developed, one has this pattern on this substrate. So that is the lithography, and this is a classical way of doing it. And lambda, this wavelength that decides the resolution, that is the minimum size or the period that one can have on this substrate. Okay, now in the same setup, if instead of having one photon come in, if we have through Hongo-Mandel effect, if we have one photon from this side, one photon from this side, then from the Hongo-Mandel effect we have either two photon going this way or two photon going that way, and there's two photon coming this way, two photon coming that way, then substrate. So in this case, what's the intensity or other coincidence intensity? So in this case, the electric fields or the field amplitude can be written, I mean this is actually applicable for the wave function, but I'm just writing using the same notations as we use for the classical fields here. So this is e to the I twice kx, because now we have two photons, e to the minus I twice kx, and then we get the intensity as 1 plus cosine 4 kx. So in this case, the intensity of the pattern that will get written on the, in fact this is not the intensity, this will be the two photon absorption probability, because now we have two photon coming this way or two photon coming this way. So we can no longer call it intensity, but this is two photon absorption probability. And with the two photon absorption probability, the pattern that gets written on this one is 1 plus cosine 8 pi x by lambda. So if we just, so this 8 pi x by lambda, we can just write a cosine 4 pi x lambda by 2. So we see just because we have two photons now, the resolution has increased by 2. That means we can write pattern twice as dense. I think these are twice as fine pattern as what we could do with the other one. So the wavelength of these photons are still the same as in the earlier case, but just because we have two entangled photons with the same wavelength, we are getting the resolution of as if we have lambda by 2 wavelengths. So this is the resolution enhancement by increasing the number of entangled photon. So although the wavelength is still lambda, but we are getting a resolution of lambda by 2. Similarly, if we can actually have n entangled photons, then using this method the resolution can actually be enhanced by a factor of n. So that's an n-fold lithographic resolution enhancement. So that is quantum lithography. Of course, with n equal to 2, this has been realized, but doing it beyond n equal to 2 in lithographic setup so far has not been possible. Of course, people are working on it. Okay, so that's quantum lithography. Let's look at the other application of quantum entanglement. This is quantum cryptography. So first, let me just quickly go through what do we mean by cryptography or classical cryptography. So cryptography is all about a party A sending a message to B in a secure manner, and in the cryptographic language, A stands for Alice, B for Bob. So for example, let's say there is a message optics, so one can encrypt this with a key, and this key can be as simple as 010110, and with that, and the rule here is that if it is 0, don't do anything. If it's 1, shift to 1 in the alphabet. So with this key we can just have O remains O, P becomes Q, T remains T, I becomes J, C becomes D, S remains S. So this is the message that then gets sent to B. Once B receives this message, B has the key, and with that key one decrypts the message and then retrieves the original message. So cryptography, the aim is to send information or message from A to B, but in this the essential thing is this key distribution, that A and B, they have to have a key that they share, and this is kept secret and nobody else knows about this key other than A and B. So of course A and B, when they come together, they can actually share a key, but in general A and B are at two distant locations, so before they can share a message they have to share a key, and this key sharing then needs to be done in a secure manner. So cryptography is all about secure key distribution. That means how A and B can generate a key among themselves that nobody else knows about, and once the key is generated, then any message can be encrypted with that key, and this encrypted message can be sent over to B, can be sent to B over even a public channel, but since only B has the key, nobody else will be able to decrypt the message. So that's the cryptography in general, and it is in general again all about secure key distribution. Once the key is distributed in a secure manner, the message can be sent over public channel without any issue. So the one older method for doing this, that means the securely doing the key, was this. This is called skylet. So this is a, for example, this is a red thing. This is a wooden block, and this has a particular shape, and this acts as a key. So any two party A and B, they will have this exact same wooden block like a cylinder, and then shape of the cylinder is the key, and both the parties A and B, they share the same cylinder, and again only they need to have these cylinder and nobody else should have the access to it. So with this, if when a message is sent, for example here this is the message, but when this message from A reaches to B, then B wraps it around the skylet, and then these letters then gets aligned. For example here, can't make sense of it, but here it becomes quantum optics is cool, and full stop. So that's the message. So when A sends a message, he writes the strip around this skylet, writes a message, and then this strip goes to B, and then again B wraps it around the same skylet and retrieves the message. So again, this was once they have the key, they have this key shared between them, there is no issue doing the secure communication. So that was one of the old methods. There are several such methods, but I just wanted to point out one of these methods. Now, the main issue in cryptography is the security or the secure key distribution. So Alice wants to send a message to Bob, and then now maybe there can be some Eve which can try to retrieve information when it is being sent from Alice to Bob. So the main issue is in cryptography is security or secure key distribution, And in classical methods, there is always a chance that if Eve gets enough information from Alice, Eve would be able to retrieve as to what the key is and again what the message is being sent. So what is the future of cryptography? The future of cryptography, it looks like, is quantum cryptography. So quantum cryptography is actually perfectly secure, and this is because of the laws of quantum mechanics. So in the sense that there could be Eve even in quantum cryptography, but if Eve gets some information about the key being sent from Alice to Bob, then because of the quantum principles, Alice and Bob would get to know that someone is actually eavesdropping, which is not possible in classical cryptography. In classical cryptography, if someone gets the information, Alice and Bob will actually not know. But in quantum cryptography, if an eavesdropper gets some information or is trying to intercept the messages being sent, Alice and Bob will actually get to know. And once they get to know, they can actually drop that particular message transformation, and that way quantum cryptography is perfectly secure. So what are those laws, what are those quantum mechanics laws that make quantum cryptography perfectly secure? So the first one is that a measurement in an incompatible basis changes the quantum state. This we have seen already, but I'll go through it one more time. So this means that, for example, in the polarization degree of freedom, we can have vertical and horizontal as one basis, and also diagonal and anti-diagonal as another basis. So we had seen that if a photon, if a state is in vertical or horizontal basis, for example, if a state is in horizontal basis, we are calling it 0, state in the vertical basis, we are calling it 1. Again, state in the diagonal basis, we are calling it 0, state in the anti-diagonal basis, 45 degree, we are calling it 1. So if a state is in vertical or horizontal, and if we make the measurement in the vertical horizontal basis, then we know for sure that we will either get H if it's 0 or we'll get V if it's 1. But suppose the state is prepared in vertical and horizontal basis, but if we make a measurement in the diagonal and anti-diagonal basis, then what happens? Then of course we won't see H and V, and now even when the state is H, we have 50% chance of seeing it as a diagonal state and 50% chance of seeing it as anti-diagonal state. Similarly, if it's actually a vertical polarization, and if we are looking at it in the diagonal anti-diagonal basis, then we have 50% chance of seeing it in as a diagonally polarized or anti-diagonally polarized photon. So this is what it means by the fact that a measurement in an incompatible basis changes the quantum state. So of course, if the state was prepared in the vertical and horizontal, if the state is prepared as either vertically polarized or horizontally polarized, and then if we make a measurement in the diagonal anti-diagonal basis, we have 50% chance of seeing it as diagonal and 50% chance of seeing it as anti-diagonal. While if we had looked at it in the horizontal vertical, then if the state was horizontal, then we would definitely see horizontal, and if the state was prepared vertical, then we would definitely see vertical. Similarly, if the state is actually prepared in diagonal anti-diagonal basis, but we look at it in the horizontal vertical basis, we of course have 50% chance of seeing it in any basis. So measurement in an incompatible basis changes the quantum. So that's the first law. The second law is what's called the no cloning theorem. This is a very powerful theorem. This says that an arbitrary state of a photon cannot be cloned, or an arbitrary quantum state cannot be cloned. So let's say we have this party A that wants to send a message to B, but then we have an eavesdropper C that has this cloning machine given by this unitary operator, this cloning machine. And this cloning machine makes, for every photon sent, it generates 2 photons with the same state. And then so if that is possible, then the C can keep 1 photon to itself and then send the other one to, and this way C would be able to get all the information being sent by A. But this theorem says that there can be no cloning machine that can do the cloning for an arbitrary quantum state. Okay, so here is how the proof goes. We are doing the proof in this 2-dimensional basis of polarization, but one can do the proof in any dimensionality. So let's say there is a unitary operator that can clone a horizontally polarized photon. So if we have 1 horizontally polarized photon coming in, this U can generate 2 horizontally polarized photons. The same the same machine can also clone for a vertically polarized photon. That means for one vertically polarized photon, the machine can generate two. Now, if a machine can generate two photons for each of vertical polarization and horizontal polarization to the same machine, let's see what happens if we send in a 45-degree polarized photon. So this 45-degree polarized photon we can write as H plus V. Now we know U acting on H gives us two horizontally polarized photon, U acting on V gives us two vertically polarized photon. So we will get this HH plus VV. But this HH plus VV is not what we intended, because this HH plus VV is not equal to H plus V and H plus V, because that's a 45, that's a 45. And if we had gotten this, then it would have meant that yes, it had cloned this 45-degree polarized photon. So this is not equal to 45-degree polarized photon. So the machine that can clone H and V, it cannot clone a 45-degree polarized photon. So that's the very simple proof of this, that shows that an arbitrary quantum state cannot be cloned. Of course, two states in a two-dimensional basis, we can clone H, we can clone V, but an arbitrary quantum state cannot be cloned. So because of these laws, we have quantum cryptography, and now we'll see there are two protocols of quantum cryptography that are most popular. One is called BB84 protocol. In the BB84 protocol, Alice sends a qubit to Bob, so it's a straight from goes from Alice to Bob, and it involves just one photon state, qubits, and there could be an Eve which can try to which will try to get information from this information transfer. The other protocol is called Eckert protocol. In this, Alice and Bob share an entangled pair of qubits, and then Alice sends a qubit to Bob by measuring her own. So what that means is that here it's a single photon based, but here it's an entangled. There are two entangled photons which Alice and Bob share, and so for example, Alice and Bob can share the state H plus VV. This can also be written in the diagonal anti-diagonal basis as DD plus AA. So in this case, BB84, Alice just sends a photon to Bob. In this one, of course, these photons, the pair of photons are being sent to Alice and Bob. Now, if Alice measures her photon in H basis, for example, in here, then Bob will get the photon in the H basis, and so on. So here, by measuring the photon, Alice sends that particular the other pair to Bob. So that way, these two are equivalent. Now, what are the 5 steps of quantum cryptography? And in fact, we are showing this correspondence because these two protocols are pretty much the same as far as these 5 steps are concerned. So what are the 5 steps of quantum cryptography? So one is called the distribution of a raw key. So in this one, Alice sends one key to Bob, a string of keys to Bob. And these keys are basically strings of 0 and 1. And here we have defined this 0 and 1. So if Alice sends photons in the horizontal, as a horizontal photon, then we call it a 0, vertical photon is 1, diagonal photon is 0, and anti-diagonal photon is 1. So that they agree upon this nomenclature before the start of the protocol. Now, the next step in the quantum cryptography is what's called the basis reconciliation. This we will get to in more detail in a bit. So in basis reconciliation, Alice and Bob, after distributing raw key, then they talk to each other and then talk about as to if they use the same basis or different basis, and that's called the basis reconciliation. And at the end of basis reconciliation, they generate what's called a sifted key. And after that, they have the sifted key, then they estimate how much error they have, and then they do the error correction, and then also what's called the privacy amplification. So these 2 steps are essentially what's quantum key distribution. These 3 steps are same as classical cryptographic scheme. This is done in even today's all the classical cryptographic schemes. So I'll basically focus on these 2 steps only. So here is one example of how Alice and Bob, they can do cryptography and at the end of it generate a secure key. So of course, Alice and Bob, they both agree to do the measurements either in the horizontal vertical basis or diagonal anti-diagonal basis. So now Alice is going to send photons to Bob either in the diagonal anti-diagonal basis or horizontal vertical basis. So again, Alice sending a photon here is equivalent to Alice measuring a photon in the Eckert protocol. So first we'll do the distribution of a raw key. Now suppose Alice chooses her basis randomly. So in this case, Alice decides that she wants to send a photon in the dA basis, and in the dA basis she wants to send a anti-diagonal photon. That's why Alice's random bit is 1. Next time Alice decides to send a photon in the horizontal vertical basis, and in the Eckert protocol it would mean that Alice decides to make the measurement in the horizontal vertical basis in the second time around. So Alice decides to send the photon in the horizontal vertical basis, and in the horizontal vertical photon Alice decides to send a 0, that means send a horizontally polarized photon, and so on. So Alice basically decides her basis randomly, and in that basis she then decides her bits also randomly, that in a given basis whether she wants to send a 0 or a 1. That means, for an example in this one, whether she wants to send a diagonal or anti-diagonal. So these are the Alice's random choice of basis, and these are the Alice's random choice of bits. So in BB84 protocol she just sends it. In the Eckert protocol she makes a measurement, and that at the time of measurement that decides her choice of random basis. Now when Bob receives the photon, Bob also makes a random choice of basis, because Bob has no idea as to which basis Alice has prepared the photon in. So Bob will also choose his basis randomly. So if and let's say these are the bases chosen by Bob, and these are the bits that Bob obtained. So this is called the distribution of a Rocky. Now once this step is done, of course Bob has no idea what basis Alice prepared her photon in, of course what bits were sent, but Bob chooses her basis randomly, and then these are the for example in this one, these are the bits that Bob obtained. Now after the distribution of the Rocky, then Alice and Bob will do what's called the basis reconciliation, and this means that Alice and Bob will get over a public channel, and then they will talk to each other and then find out what were the instances when they happened to use the same basis, and what were the instances when they happened to use different bases. Of course they chose it randomly, but in a few they happen to choose the same basis, for example here, and so on. So in whichever instance they happen to choose the same basis, they will keep those measurement results. But whenever they happen to choose a different basis, they will actually throw that particular measurement result away. So for example, in the first one, Alice chose dA, Bob chose HB, so that's an incompatible set of bases, so they will throw that result away. In the second one, both Alice and Bob happen to choose HB, so they will keep it. Third one, they will throw it away. Fourth one, throw away. Fifth one, they keep, and so on. So this way they basically throw away whenever these two bases are different, and they keep the results when the two bases are the same. So at the end of it, they have this string of bits 0, 0, 1, 1, that they know for sure that these results, of course they never announce what exactly the bits they have, but they know for sure that if they had chosen the same basis, or whichever instances they happen to choose the same basis, those measurements result would be perfectly correlated. Of course, if they choose a different basis, incompatible basis, the results could be correlated. For example, here it's 1, 1, or they could be uncorrelated, that's here 0 and 1. But they will throw away everything, because they don't know in which instance it could be correlated, in which instance it is not. So at the end of basis reconciliation, basically Alice and Bob, they end up with a string of these 0 and 1s that they know for sure are completely correlated. So that's called the sifted bits. So these were the random bits, and that's called the sifted bits 0, 0, 1, 1. So if there was no Eve in the system, so if there was no measurement done by the Eve in the system, then at the end of it, Alice and Bob would end up with this bits 0, 0, 1, 1. Of course, in this example, they end up with just four numbers, but if it's in the actual quantum cryptography, this string could be 10,000 digits long, and in that case, maybe after basis reconciliation, they end up with at least 1,000 or 2,000 and so on. So this is just a kind of an example. So at the end of basis reconciliation, if there is no eavesdropping, then this will be perfectly correlated string of numbers. But if there is an Eve in the system, and then if the Eve tries to make some measurement, and of course Eve has no idea at the time of measurement as to which basis Alice has sent the photon in. So of course Eve will choose the basis randomly, and so the bits that Eve will get will also be completely uncorrelated. So if Eve does a measurement, then that will change this correlation property here. Then just the fact that Eve makes a measurement here, or clones or anything, it will introduce error in this shifted bit. So in the next step in quantum cryptography, that's the error estimation. Then Alice and Bob, I mean, now here we have only 4 numbers, but in an actual quantum cryptography there could be thousands or millions of numbers, and out of those million number, Alice and Bob will pick some and then estimate the error, and then after that the error is corrected, and then there's also called the privacy amplification. But the main quantum aspect in the quantum cryptography is this generation of this shifted bits. And that's through this scheme, and that's called the quantum key distribution scheme. Okay, so again, as I said, this is perfectly secure because of the laws of quantum mechanics, and because of which, if Eves makes a measurement, Alice and Bob would get to know by analyzing if they have any error in their shifted bits. And if the errors are within some limit, then of course that can be corrected, but if the errors are beyond that limit, then Alice and Bob will start over. And until they get the error within the limit that can be fixed, Alice and Bob will keep doing this same protocol until they reach that limit, and in that case they will say that the key distribution is complete, and then they will keep that last set. Quantum cryptography has been demonstrated in 2000. There was this demonstration over optical fiber. I'm not going to go through the details of this experiment. And then so this was in 2000, and this was the object encrypted and then decrypted. In 2000, it was demonstrated almost over 144 kilometer. In 2017, this was demonstrated between a satellite to a ground station. So this is still a work in process. This is not complete, but this is one of the quantum technologies that seems that it will come into practice maybe within the next few years. So we will stop here today. In the next lecture, that will be the last lecture, we'll look at one more application of quantum entanglement. So we'll stop here today. Thank you.